To really help make scheduling more concrete for you, let's take a look at the scheduling code in our XV6 educational operating system. It's going to be somewhat simple, like significantly more simple than the Linux kernel, which we'll also take a look at sort of like later. But it should sort of give you a feel for all the different data structures involved, all the different parts that coordinate together to actually have scheduling in an operating system. So let's take a look. Here we're going to look at the x86 code, and I'm looking at processor.c. As we sort of like go through this, like I'll explain some of the data structures that XV6 uses, and then from the function we'll see what is actually being used, and we'll sort of like go and go back and look at some of the data structures. But one of the first things I want to highlight is basically this P table, which is processor table, and what it's showing is that there is a list of different processes. We can run a maximum of like n processes on our system, and then there is a lock associated with this. We'll do concurrency and sort of locking a little bit later in the course, but typically, anytime you have state that multiple processors or processes will be touching, you want to make sure that they update it in an orderly fashion. So only one person at a time is sort of like writing to this table, and that's really what the lock is for. So it ensures that whoever holds the lock is the one person who is writing to the processor table. The other people just have to wait for the lock in order to write to it. Let's take a look at like what this looks like, the process thing. By the way, like what I just did is I used tags to move from sort of like the place where it's being used to the actual function definition, and this is something that I highly encourage all of you to sort of like do. So on whatever system you're on, Linux, Mac OS X, or Windows, you will have some version of like C tags or E tags, and what this really does is it creates an index of like where different data structures and functions are all placed in your code, so that while you're browsing the code and you suddenly want to go to sort of like the definition of like this structure, you can sort of like move there pretty quickly. Learning to navigate code in this manner is one of like the chief things you would need as you do systems research and as you build systems. Whatever your favorite processor is, like Vim, Emacs, whatever, like make sure that you understand how to use tags and how to move from where a variable is used to its definition and back pretty quickly using keyboard shortcuts. So anyway, so back to like what we were doing. So here is the process as defined by XV6, and like there are some stuff that's like fairly easy to understand. So for example, there is the parent that we just talked about, whichever process spawned this process. And initially, like there will be only a single process called init, and everything will be the children of that process. There is the ID of that process. So every process in the system has a unique ID. If you use Linux, you already would have seen this, like when you're killing a process, you would use the ID to sort of do that. And we've already seen this a little bit previously in other classes too. So trap frame is basically like how your arguments are set out as you do your context switches. So for example, look at all the registers that you need to put on your stack as you move from like one process to another, right? So your EDI, ESI, EBP, all these different registers will be saved as part of your trap frame, and this trap frame will be put on part of your stack, right? So that's the trap frame, and then context is like all the different things you need in order to switch between process states. So for example, let's go look at like what's in context. So different registers, right? So there's a difference between registers that you would need as you switch between functions within the same process, and registers that you would need as you move from one process to another through the kernel. So the context here is all the registers that x86 and GCC together agree that should be saved when a process is sort of like context switched and another process is going to execute. To put it another way, these are all the different things which are going to be the same at the point at which you start a context switch and when you return from a context switch. So for some of these registers we already know about. EIP is the instruction pointer. EBP is basically your stack frame pointer. So it points to the top of your frame, and you can reference all the different things inside a frame by using the base pointer. And we have like a number of like general purpose registers that you're going to use. So all these things are part of the context, and when you do a context switch, these things should be saved, then be restored whenever you do, and when you start and restore a process. Anyway, so where were we? So here we are. So we're looking at the different things in a context, and this basically is like a flag which says whether this process should be killed. Now, if you've worked with Linux before, you know that you can send a signal to a process, and then on receiving that signal, the process will kill itself, basically. In x86, it doesn't really work that way. So when you want to kill a process, what happens is when you send a signal to this process, this particular flag gets set. And at some later point of time, x86 will notice that this flag has been set, and then it will kill the process. The reason it doesn't so synchronously is because it is fairly complex to kill a process in the middle of like whatever processing it may be doing. For example, it may be in the middle of a context switch. It may be like turning off interrupts to do some processing. It may be doing some fairly complex stuff. So x86 does not guarantee that when you send a signal to kill a process, it will do so immediately. Only that a flag will be set, and at some later point of time, the process will notice this flag and then kill itself. So it's sort of like an interesting difference between Linux and x86 as we see. And there are, of course, variables which denote like what are all the open files, the current directory in which the process is executing, and so on. And for debugging purposes, you can actually have a name for each process. So you can say shell and init and so on. And when you're looking at the process table, this actually helps you debug like, oh, what are all the processes that are currently running? So anyway, so these are all the different things that make up a process in x86. So far, process to us has been the sort of like very abstract thing. But from this code, what you can see is that process is actually sort of like a bunch of variables, right? Encapsulated together such that it keeps track of like your stack, your instruction pointer, your registers, all of this other stuff. So whatever things you conceptually think of as like, like I'm executing a program or a process, these are all the things associated with that. When you group that together, that's really what a process is. So hopefully that makes a process sort of like more concrete to you. So to come back to our initial screen, so we have the process table in x86, and we can have a certain number of processes. I forgot what this number is. So you can have 64 processes in x86. Anyway, so let's now go take a look at schedule. Let's see. The zombie state, here we go. So this is the scheduler, the CPU scheduler that is used by x86. Now you can run x86 with multiple different processors. So a copy of this scheduler will be running on each processor that x86 has. So let's sort of like take a quick look at like what is going on in the scheduler. So you have a pointer to a process, and then you have the CPU struct. So let's go take a look at like what what's inside a CPU, right? Remember that x86 is operating on top of emulated hardware, right? In our case, we use QEMU to emulate like a machine on top of which we're going to run x86. So of course, x86 can also run on like actual bare metal hardware. And CPU is all the different hardware state that sort of like uniquely identifies a CPU and stores the context for scheduling. So here, your APIC ID is basically a hardware ID that is unique for each processor in a system. So if you have two processes in a system, your APIC IDs may be like 0 and 1 or 1 and 2 and so on. So using your APIC ID, you can uniquely identify each processor in a system. And if you look at it, like there's a bunch of other stuff that's grouped together with the CPU, the process that is currently running on this particular CPU, whether interrupts are enabled or not, sort of like unfortunately named variable, the state that's required for your scheduler, and things like, like your interrupt table and your global descriptor table, we're not going to worry about for now. When we look at memory management, we'll come back and sort of like look at this. Right? So that's really what a CPU is. Again, a bunch of different variables encapsulating the state required to emulate a CPU. So coming back to our scheduler code, what we first do is we figure out like which CPU is this scheduler running on, right? So all my CPU does is it goes into your APIC, your hardware, and then it gets the ID of the processor, and then it just goes through the CPU table, right? And it finds out which CPU has the same ID as this processor that I'm on, and it returns that CPU. So a way to think about this is there is a mapping between your CPUs and your hardware processors. So processor with ID 100 may be CPU 0, ID 101 may be CPU 1. So all this really does is like, what processor am I running on, what is the CPU associated with that processor, and then like returns that CPU, right? Basically, long story short, what this does is it gets you the CPU that you're currently running on, right? And initially we said that the processor that's going to be running on this CPU is going to be 0 or null. So there's nothing running on the CPU initially, right? And then all the scheduler does, sort of like in an infinite loop, is it acquires a lock over the process table. And the reason it does this is because your processor table can be changing all the time, right? What your processor table really contains is a list of like currently running processes, and so a process may start, a process may die, and so you want to make sure that when you are looking at like what process is there, you want a stable state. So if you don't have a lock while you're looking at it, it may change from underneath you. So you get a lock first, right? So you acquire a lock. And then what you do is you just go through this table of like processes, and then you check for the state of a process. As we talked about, a process can have different states, and it's runnable if it. That means that it can then be put on a processor. So it's not waiting for I/O. All its initialization is done. All of that is in order. So you can just take and run this particular process, right? So it waits for it waits until it hits a process that has state runnable. And then this is where sort of like the actual the magic starts to take place, right? So first thing it does is it sets the process that is currently running on the CPU to be this process P, right? And then here what it's doing is it's setting up the memory for the process. We're not going to look at this right now. We'll come back to it in the memory management part of it. It sets the process's state to be running. Previously, this state was runnable, and then here's really the interesting part of it, right? It does a context switch, right? It does a context switch from this context, which is like inside the scheduler, into the process's context. So the process could have already run, and it's like stopped at some point, and then it will continue running at that point. And so when the process finishes its time slice, or like it finishes executing, it will try to switch back to the scheduler, and the scheduler will run again from here. So this is sort of like an interesting and like funky part of this whole scheduler thing. So at this point, you're just saying stop everything in the scheduler, like move to process P. So you're stopping everything. You're like your schedule execution stops here, and then you're moving from the scheduler to process P. Then whatever the context says, whatever the instruction pointer says, you're going to start running process P. At some later point of time, process P will be interrupted by the timer interrupt, or it's finished executing or whatever. Then it will try to move back to the scheduler, and then it will do a context switch, and then it will do a reverse context switch, basically. Like it will move from this P context to the scheduler, and then we return here, and then we continue running. So it's kind of like a very non-linear sequence of operations. We are sort of like used to like going like instruction 1, instruction 2, instruction 3, but here it's like sort of like jumping all over the place, and that makes it a little bit complicated. So anyway, so we get back here, and then the process is not running anymore. So we say the process, like there's nothing running on this current processor, and then we just go back, and then we try to like once again find a process. So this is a high level of like how the CPU scheduler works in XV6. So next we'll sort of like take a look at like the context switch code again, and then we'll talk about like what policy is actually being implemented in XV6.